Welcome to the Cosmic Pie Podcast, Episode 10, Season 4. I'm your host, Wayne Barkhouse. We are streaming live from the campus of the University of North Dakota here in Grand Forks, North Dakota. Notice I'm by myself today. This is a bit of an experiment. Robert is off this week. We are celebrating, if you like, spring break here at the university. And so today we're going to try to get by with just myself. So we'll see how it goes. If you do have any comments or chats that you would like me to read or answer while we do the podcast, feel free to use that feature. Also, don't forget to give us a thumbs up if you like this podcast. If you don't like it, don't give us a thumbs down. Always be positive. That's how we like it here. Okay, so first of all, a disclaimer. So anything that I say is my own personal opinion and not necessarily that of the university or of our Department of Physics and Astrophysics, or of the United States government, or of the planet Earth, or of the universe, or anything else. So with that out of the way, the other thing I wanted to mention before we start here is that we do upload our podcast the next day on Spotify. So if you would like to see it on Spotify rather than watch it on YouTube, please feel free to do that. Now, the first thing I wanted to get into to talk about is some interesting information that we kind of talked about a couple of years ago, so roughly almost 2 years ago. There was an asteroid that was detected. It has a proper name, Asteroid 2024, YR4. It had a very tiny chance of colliding with the Earth. Now, initially, people were getting a little bit worried about this asteroid when it was first discovered. And the reason for that, anytime that you make new observations of things like asteroids, you really don't have sort of a good understanding of the exact orbit that these objects are in. And so because of that, there was a very small, but not zero, chance that would collide with the Earth in 2032. And you think about it, that's only 6 years away. It's not a lot of time to prepare. And how would you prepare for such a thing? Well, you can imagine that we would take our space program and develop some kind of rocket technology that has pooled together our resources across the planet itself and maybe go near the asteroid and maybe detonate a nuclear weapon, not at the asteroid itself because it was large enough, hard to say if it would destroy it, might, but try to give it at least a gentle nudge. And if you catch it early enough, then maybe by the time the asteroid is in the vicinity of the Earth in 2032, it would actually miss the Earth and not hit us. So there are a couple of things that people are thinking about what to do with asteroid mitigation. So some of these involve, as I mentioned, the use of nuclear weapons. The other thing involves just putting an object nearby that has a mass. And because any object that has a mass is going to be attracted to any other object that has a mass through the gravitational force. If you're able to put sort of a massive object near the vicinity of an asteroid and you're able to maintain that sort of separation for over the course of several years, you could ever so slightly redirect the path of that asteroid so that it would not, hit the target, i.e. the Earth, for example, or maybe it was designed, or it's going to hit the moon or something, and in the distant future we have bases on the moon, and so there was going to be an issue with that. Then you want to be able to redirect, if you like, these bowling balls that are roaming around our solar system. Now, with follow-up observations of this particular object, we discovered that it was going to miss the Earth. So the uncertainty in the position of this asteroid reached a point where we could say for 100% certainty that it would not collide with the Earth. But the interesting thing was that it would collide with the moon. At least there was a small chance of this happening. In fact, we talked about it on a previous podcast about what are the predicted sort of impact sites on the moon itself. And you can see that from this slide in the yellow dots. These are the predicted areas and potentially where the asteroid could hit. Of course, there's a large uncertainty here, and we need to refine the orbit even more so in order to, number one, say for sure that this asteroid will hit the moon in December of 2032. And if it is going to hit the moon, can we narrow down a little closer where the impact site would be? And by 2032, remember, we're getting into that time frame where we're going to be landing on the moon itself. And if it gets close to one of the areas we want to land on, that could be an issue. So you can imagine an asteroid striking the surface of the moon and then throwing up all kinds of debris. And if that debris rains down in different directions, how do you know that some of that is not going to fall near where you have astronauts actively working on the surface of the moon itself? So obviously that can be an issue. So we have to worry about those. We have to worry about those sort of things. Now, why it's in the news now is because recent observations that were done near the end of February, so in particular on February the 26th of this year, and these observations are of the asteroid taken by the James Webb Space Telescope. From these type of observations and noting the position of the asteroid relative to the background of stars, so in these stars we accurately know their positions very well. And because of that, we'd be able to come up with a much better, if you like, refinement of the orbit of this asteroid and what it will do in December of 2032. And the calculations show us that the asteroid will actually miss the moon by about 20,000 kilometers or so. So it's going to be interesting as we watch this asteroid pass very close to the moon in 6 years from now, but not hit the moon. Now, there are some advantages, I guess, and disadvantages for this, depending on how you want to look at this. For example, there was a paper that was published about a year or so ago that indicated that if this asteroid did hit the moon in 32, that there is a chance that some debris would be ejected from the surface of the moon and actually hit the Earth. So that would be something, of course, we'd want to keep an eye on. But the other, so having it not now hitting the moon in 6 years, that's a positive thing as far as that's concerned. But the negative thing in some sense is the fact that you are not able to kind of watch to see what happens to an asteroid when it actually hits the moon. You're going to gouge out some type of crater at some depth, unknown of course, and that depth of that crater could expose some really fresh material buried under the surface of the moon itself, and you never know what that can kind of give you. It would cough up some material in which we could maybe take a sample of it and analyze it in situ, if you like, to figure out what is buried, several hundred meters potentially under the surface of the moon itself, and have some kind of direct measurement. And there are other things you can think of too, why it would be a disadvantage of the asteroid not hitting the moon, but at least from a scientific point of view, there are obviously negatives and positives that go with all of this. So as it turns out, then we are not, fortunately or unfortunately, depending on how you want to think about it, having an asteroid collide with the moon 2032. Of course, with asteroids, you never know what's going to happen, and that's why we got to keep an eye on them. I remember a couple decades ago, so this would have been in sort of the late 90s, some astronomers, and very few of them, were going around giving colloquia, and they would make a point of saying, the number of people that are actually employed right now to look for potential Earth-striking asteroids actually numbers less than the number of people that work in a typical McDonald's restaurant at a given moment. And when you think about it, that's like, how could we do that? We need to have hundreds and hundreds of people, surveying the sky looking for these asteroids. Well, the United States government and other governments around the world since that time have looked at this problem, realized that there could be a potential issue. And the first thing you want to do, of course, is to map out the orbital paths of all the asteroids that are large enough to cause severe damage here on the Earth. In fact, some of them could be so large, as we know, let's say several miles in size, that there's basically global killers, right? They would wipe out everything on the planet Earth. The only thing that would survive would be probably cockroaches and ticks or something like that. And depending, of course, where the asteroid actually would impact the Earth. And so you'd want to be able to, number one, map out any potential Earth impactors. Number two, you want to concentrate on some type of mitigation system, as I mentioned already, where you could do something about it if you had enough leeway time. So if, for example, we would know that an asteroid had a good chance of striking the Earth, let's say in 20 years from now, that's enough time that we should be able to come up with something that would, allow us to save the Earth, right? To, Call up people like Bruce Willis, drill holes in the asteroids, plant nuclear weapons, ignite them. Of course, if the asteroid is really large, the explosion of even our largest atomic weapons are not really going to do much. But there must be ways that we could develop, and like as I mentioned already, to deviate the path ever so slightly. If you change it just a little bit, that change sort of compounds over time. So after 20 years from now, the asteroid would miss the Earth, for example, by a large amount. Now, you might think that all you had to do was survey the sky once and then you're done, but unfortunately, that is not the case. Asteroids can change their orbits on their own, and there are a couple different sort of physical effects here, and I don't mean by direct collision. The space, if you think of where the asteroid belt is today, the asteroids are predominantly found between the orbits of Mars and Jupiter. And if you think of that as let's say a large donut, right, the center of which would be the sun, and the surface of the donut, the rim of the donut, if you like, lies between Mars and Jupiter. That space that the asteroids are in, that's actually quite large. That's a large volume. And it's not like Star Wars, unfortunately, in our solar system anyways, where you try to pass through the asteroid belt and you got to shoot all the asteroids that are in front of you to get them out of your way so that you can safely pass through. It's not like that at all. And we know that because, number one, we can observe that part of the sky with telescopes, but also don't forget we've actually sent spacecraft through that region. These spacecraft, of course, are unmanned, but they would include things like Pioneer 10 and 11. This would include Voyager 1 and 2. They would include the New Horizons spacecraft, and also any spacecraft that we would send on the Jupiter and Saturn and beyond all had to pass through that region of where the asteroid belt is located. And as far as I know, not a single one of them has collided with a particle that was large enough to cause any damage to the spacecraft itself. So that's the story is, and that we got to keep looking for these things, because one of the physical effects that can happen is the absorption of light coming from the sun. And when an asteroid, for example, absorbs sunlight, it will want to re-emit that energy, usually in the infrared. And that emission of infrared light acts sort of like a small rocket thruster. And so it can change, given enough time, and this could be even hundreds of thousands of millions of years. Asteroids can change their orbits all on their own. And because of that, you never know for certainty when an asteroid happens to be now on a path that would allow it to hit the Earth. And so it's not like we're observed once and we're done. We're going to have to continue to do this essentially forever, right? Is to keep an eye on all of these asteroids in our solar system to make sure that we catch them early enough to avoid any type of direct collision. Now, recently there's been a study that came out that analyzed what we did a couple of years ago with the NASA DART mission. And this, if you recall, we launched a projectile that hit the surface of a small satellite that's in orbit around Dimorphos. And the impactor actually changed the orbit ever so slightly of that satellite. So it turns out that some fraction, somewhere around 15% of the asteroids, as far as we know today, we haven't looked at all the asteroids that are in our solar system, of course, but roughly on the order of 15 or so are so-called binary asteroids. This means you have usually the main asteroid, which contains most of the mass, and then you have a smaller asteroid, and both of these objects would be orbiting what we call the center of mass of the system itself. And so in this particular case with Dimorphos, then, we knew of the existence of the satellite asteroid, and we could track its motion very accurately. And then when we hit the asteroid, the smaller one, the satellite of the main asteroid, we can then watch it to see how it moved, how it responded to that impact. And it did indeed change its orbit. So this shows us that with enough kinetic energy of motion, that we can at least alter ever so slightly the orbital path, at least some asteroids. Of course, that depends on the mass of these asteroids. And so that's one way we may develop in the future to try to make sure that none of these bodies hit the Earth. And the other thing that came out recently, this is in a paper that was published in the Planetary Science Journal, is that close monitoring of the satellite to Dimorphos and the main body itself showed there was actually sort of a spray of material that sort of propagated from one side to the other, that is, from one asteroid to the other. So these binary asteroids at least can interchange material, which is really interesting in the sense that it probably doesn't take a lot to loosen up some of the material off the surface of most of these asteroids. In fact, that gets to the idea where we have this kind of loose grains, that are just sitting there, and it doesn't take much of an impact to kind of shake them up. In fact, we've seen this already. The Japanese, with their Hayabusa mission, tried to extend out anchors into the surface of the asteroid that they were looking at directly and taking direct measurements, and they couldn't do that. They couldn't get a good fix on the surface of the asteroid because it was essentially a rubble pile. There was nothing really to get a hold of, if you like, so there's no solid surface for at least some of these asteroids. So it's very interesting. Asteroid science on itself is something that we need to worry about in the future, and a way to do that, of course, is to go to these asteroids directly and to try to land or at least scoop up the material to get a better idea of the composition of these asteroids, and therefore allowing us what is the best way that we can sort of minimize the threat to our home planet. Now, as sort of an update to something we've talked about extensively in the past, there's actually been several papers that's been published recently. In fact, I noticed there was like 3 or 4 of them, it seemed like, that came out even today, of observations that were done of the Comet 3I Atlas. And as you may recall, this is the comet where some people, at least on the internet and not on the internet, and that is they did public TV interviews and stuff, suggested that this comet could be a probe or an alien spacecraft. So, of course, that got everybody's attention because it was a scientist, somebody who has a PhD in science is saying this stuff. You probably want to listen. Turns out the odds of this happening was extremely small. It wasn't zero. I mean, you can never say that this would be impossible, but it's just that the chance of it was very small. And all observations that were done on this object show that this object is nothing more than a comet itself. But when I say the phrase nothing more, that's kind of a disservice in the sense that the comet itself has some unusual properties. For example, we know that the comet has a very sort of high level or ratio of what we call deuterium to hydrogen. So remember, hydrogen in the most common form, it has 1 proton in the nucleus, and then in orbiting outside of the nucleus, if we want to think of that way, we find 1 electron, and that would be, electrically neutral type of hydrogen atom. But there are certain conditions under which hydrogen could find itself in its nucleus having not just 1 proton, but 1 proton and 1 neutron. And this would be a different, what we call, isotope of that atom. In this case, we give it a proper name. It's called deuterium. And of course, you can go one step above that. You can take 2 neutrons and put it in the center of the hydrogen atom, and you'd have tritium. So what we look at in order to try to understand what is the potential source of things like water here on the Earth is to measure what we call the deuterium to hydrogen ratio. How much of this sort of rare isotope of hydrogen, which has a neutron in its center and all of the hydrogen atoms, do we have compared to the amount of sort of ordinary or common hydrogen where you just have a single proton in the nucleus of the atom itself? Now, it turns out for the Comet 3I Atlas that the ratio of deuterium to hydrogen is about 30 times more than the sort of average comet that we find in our solar system. 30 times. That's not a little bit, right? That's a lot. Now, if you compare that to Earth's oceans, for example, the water, we find that the deuterium to hydrogen ratio in Earth's water, for the comet, it's about 40 times greater. So 40 times greater than what we have in the water that you drink, essentially, and 30 times greater than what we find for the comets in our solar system. So that is clearly unusual. So why is that? Well, one of the things that probably is what it's telling us is something about the environment in which this comet actually formed. So the environment was such that it was formed in a region, and wherever that region is in our galaxy, we don't know and can't say for sure. But it formed somewhere where we had an unusually high deuterium to hydrogen ratio compared to what we have here locally in our solar system. Now, the other thing that we discovered is, and this is another paper that came out today, is if you look at the isotope ratio of carbon, in this case carbon-12 to carbon-13, it is also a bit higher than what we find in the comets in our solar system, and also it's sort of higher than the average value of what we find in interstellar medium, that is the raw ingredients that we have spread out in our galaxy, for example, the Milky Way, from which stars would form from, and planets and things like asteroids that we talked about already, and even comets. And so it's slightly higher for Comet 3i Atlas than we find locally around us, and also, like as I mentioned, molecular clouds that we observe. But there's also something else, and that's what this slide is showing you, that if we look at the measurement of what we call methanol, so this is alcohol, to hydrogen cyanide, that ratio is also extremely high. In fact, we get numbers, and these numbers vary from about 124 to about 79. So the ratio, by the way, methanol, that's the type of alcohol you do not want to drink, right? That's the one that makes you go blind. So stay away from that. But this methanol to hydrogen cyanide ratio is extremely high. In fact, it is the highest ratio of methanol to HCN that we've ever observed before in any comets. So this is something else that you can put as a label then that makes Comet 3i Atlas unusual in that sense. Now, what that's telling us probably is the fact that, if you didn't know the orbit of the comet, and I just gave you all these numbers, these measurements that have been made, and I ask you, what do you think? Is this a comet in our solar system, or do you think this comet is from somewhere else? And given the observations that you'd have at your disposal, you would probably guess, well, it's unusual, and it seems not to be like the normal comets in our solar system, so I'm going to take a shot and say this is from some other solar system, and without even telling you the type of orbit it's in, and clearly you'd be right. And of course, the orbit is what gives it to us right away that is the case, because it's not on a bound orbit. It has too much energy. It's going too fast to go into orbit around the sun. So it was inbound and really didn't get close to the sun. It went out close to the orbit of Mars as it swung near its closest approach to our sun. And then it's on its way out of the solar system to never return, of course. And some people suggest that, well, there's a lot of unusual things going on with this comet. Why don't we put together, some rockets and let's launch a probe to get to the comet? That turns out to be extremely difficult given how fast it's traveling outbound out of our solar system. If we had infinite amount of money, that is, if you get, somebody who has billions and billions and billions of dollars, Elon Musk, if you could put your money together and develop, maybe use the very powerful, Falcon Heavy rocket, and you put on board something that has the smallest amount of mass possible in order to allow you then to attain, a high rate of speed. You probably can chase it down, but it's going to take many years to do so. It's not out of the picture, but you can do it. And it's going to just take a lot of effort, which means a lot of money. And so who's willing to cough up that money? That's the thing. So we could catch it, but who's going to do that? What you might want to do is do something else. That something else is wait for the next one. And you might think, well, why do I need to wait for the next one? And maybe that'll be 50 years or 100 years from now. Well, the thing to note is that starting very, very soon, that is starting maybe the end of this month, so maybe in April, we have the Vera Rubin telescope down in Chile that's going to survey the whole southern sky every 3 nights and continue doing that. Every 3 nights, observe it again and again, every night after night after night after night after night. And then you can add all that data together and you can look for things that change, over the course of the observations. And this project is at least going to continue for about 10 years or so. So it is expected that we could literally detect tens, if not hundreds, of these type of objects like Oumuamua, which was the first interstellar object detected, which seems to have properties more associated with an asteroid than it does a comet. Or we could detect things like Comet Borisov, which had all of the indications that it is a comet. It had a coma and a bit of a tail associated with it, or even Comet 3I Atlas type of objects. So these are things that came from a different star system. They came from a different part of our galaxy and happened to get close enough to our sun that it passed by our sun and then back out again. So potentially, we should be able to detect lots of these things. And of course, because we've seen 3 of them in recent times, people are going to be out there looking for these objects. So the data is going to be analyzed to death, looking for any new interstellar objects. And you can imagine that if you had a spacecraft, which the European Space Agency was looking at planning to do here, is you could have maybe twin spacecraft already in orbit around the sun, and just having them sort of on station keeping, going on their orbit, just waiting and waiting until a new object comes through our solar system from an interstellar type object, and then have these spacecraft, if the orbit is right, to catch up to these objects to be able to make observations close up of these objects, whether they're asteroids from somewhere else or comets. So we'll see how that develops in the future. But to be fair, you can definitely say that Comet 3I Atlas is unusual in the sense of a comet in terms of its composition. But there's no evidence, for example, that it is or an alien spacecraft, so we can definitely put that to rest. Now, the other big item that came in the news recently is we're going to get a data dump coming up here fairly soon. And this data dump is from the LIGO type of gravitational wave detectors that had been running here on the Earth, with our first detection having been done, over 10 years ago, back in 2015. Now, there have been several catalogs of these gravitational wave sources that had been released, and just to kind of explain them out what they are. Way back, I'm sure you remember this, way back in 1915, so a little over 100 years ago, when the general theory of relativity was published by Albert Einstein. One of the things that people looked at, including Einstein, and he kind of changed his mind on this, he waffled back and forth a little bit, was the fact that if the general theory of relativity is actually true, it's an accurate description of reality, if you like, then out of that are predictions. And one of the predictions is that accelerating objects, so think of the Earth, for example, going around the sun in its orbit, because the Earth is always changing its direction. It doesn't matter if you think of a circular orbit or if an elliptical type of orbit. Because the object, like the Earth, is constantly changing its direction, that means it has a constantly changing velocity. Because velocity has 2 components, as I'm sure you're aware of, both speed and direction. So if both or at least one of those components is changing, that's a changing velocity. And a changing velocity is an acceleration. So an object like the Earth, as it accelerates in its orbit as it goes around the sun, actually produces ripples in the fabric of space-time. Now, these ripples, we call them gravitational waves. Now, these waves pass through all material bodies. That is, if a wave passes by the Earth doesn't diffract or reflect the wave. These waves will pass right through the Earth itself, as if the Earth's not even there. Now, most sources of gravitational waves, and it turns out that the greater the mass of the objects that are accelerating, the greater will be these gravitational waves. So the typical sources of gravitational waves that we would have any hope at all detecting here on Earth are things like merging black holes. So you could get in a situation where we have, like we have in star systems, where more than probably 50% of all stars in our galaxy, and probably other galaxies as well, consist of at least 2 or more stars in orbit around their center of mass. So it's not unusual that you'd have what's called a binary star system. And if these 2 stars are really massive, so that their end states turn into black holes, you can end up in this situation where you have a binary black hole system. That is 2 black holes that are in orbit around each other. And what could happen over time is, through the release of gravitational waves, that allows energy to escape the system. And that release or loss of energy shows up as the two black holes getting closer and closer and closer together. Ultimately, what happens is that they would merge and form a single black hole. Now, if you had, let's say as an example, two black holes, each of them, let's say 50 times the mass of our sun, and if these two black holes were to merge, they do not create a black hole. That's the sum of the two masses, which in this case would be 100 solar masses. They would create a black hole that has less mass than that, maybe on the order of, like 90 solar masses or so. And you might say, well, what happened to the other 10 solar masses? That other 10 solar masses actually went into the actual creation of the burst of gravitational waves that occurred when these two black holes actually merged. In other words, it takes a lot of energy to shake space, to stretch it and to squeeze it. And because, or at least you could think of energy and mass being equivalent, the famous E equals mc squared equation from Albert Einstein, to get the amount of energy that you need to generate a burst of gravitational waves on the order that we're talking about here with two massive black holes, that takes a lot of mass. So that would take many solar masses of material for this to occur. Now, what happens when a gravitational wave passes by a position in space, let's say the Earth, and these waves are coming from a source that's, let's say, 1 billion light years away. So it's not nearby, obviously, very, very far away. Well, what would happen is as these waves pass by and through the Earth, they cause space to ever so slightly stretch in one dimension and then ever so slightly squeeze in another dimension. So you get both the stretching out and the squeezing of space itself. Now, because the sort of average distance of these sources of gravitational waves is hundreds of millions to billions of light years away, by that time the wave washes through the Earth, the amount of stretching and squeezing is so tiny, we expect on average, and we can actually do the measurements, the observations now, so we don't have to guess, but the sort of stretching and squeezing, the amount that you get, is typically about 1/10,000th the size of a proton. In other words, the amount of stretching and squeezing is so minute, it's essentially negligible, and you never have to worry about that. And it's not only that, you wouldn't even know the gravitational wave passed through your body. It would have zero impact on you. Now, that also means that it's going to be extremely hard to detect these. So how the heck then could you detect these gravitational waves? Well, that was a major puzzle until 2015. There were several attempts to detect gravitational waves that just didn't work. The experiments that people devised were not sensitive enough to detect such a minute amount of stretching and squeezing of space itself. And by the way, this disturbance propagates at the speed of light. Now, the other thing is, it's a way to envision, I guess, the change in the amount or strength of a gravitational wave is with distance. It's kind of think about, let's say you're on the shore of a very large lake, a couple miles in width or something, and you're fishing. And then you notice in the far distance you see a boat that's going by at a fairly high rate of speed. By the time the waves reach you, 2 miles away from the path of that speedboat, those waves are not very high in amplitude. They're very low. As you could barely tell if you're far enough away from the source of the waves that there's all of a sudden a disturbance in the water if the water is fairly still before the boat went by. So over distance, and these amplitudes get smaller and smaller and smaller. In fact, they go like 1 over the distance. So if you double the distance, you half the amplitude of these gravitational waves. So if you're detecting gravitational waves coming from a source that's sort of 1 billion light years away, they're going to be essentially almost negligible at the time they reach you. So how do you know they exist? And remember, this is a prediction from the general theory of relativity. And anytime that we look at theories of science, and remember, a theory is not just, I have an idea. That's a hypothesis. That's an idea. right? A theory in science is that you have some kind of a idea or hypothesis that you've worked on, and you've accumulated some type of theoretical and experimental evidence that support that idea or that hypothesis to the point now where it becomes a theory. So a theory then has lots of supporting evidence behind it in science. So this theory of the general theory of relativity then, one of the predictions is the existence of these gravitational waves, but they're so elusive. How the heck are you going to detect them? And by the way, if you do develop the technology to detect these gravitational waves and they're just not there, they don't exist in nature, then that is a major strike against the general theory of relativity. That would tell us that there's something wrong with that theory, that we need to modify it or replace it with something that's better. So when we looked for these gravitational waves, we had to develop that technology. And what we ended up doing, and here's kind of a simplified way of looking at it in this slide, is we send light, let's say in the form of lasers, down one length of a leg that's been evacuated as much as possible, so they won't have any interference with molecules and dust particles and atoms that's in these tubes. These tubes, as you see here, are sort of L in shape, so they're perpendicular to each other, and their lengths are on the order of about 4 kilometers. And what happens is, where the two legs join, we have a source of light, like a laser. A laser beam goes down one length of the leg and also down the other. Now, there are reflecting mirrors that are located at the end of these legs, and the light then reflects off of those mirrors and comes back towards the laser. Of course, in reality, this happens multiple, thousands and thousands of times, before it gets, recombined, as we say. But let's just vision it as just two rays of light, each going down the separate leg, reflects off the mirror, comes back to the starting point. And the distance of these legs, that is the length of the legs, the distance that the light ultimately has traveled, can vary a little bit by changing the position of the reflecting mirrors, let's say. And you can set up the mirrors such that by the time the light goes down the two legs and then comes back to the starting point, it combines in such a way that it perfectly cancels each other out, what we call in optics destructive interference. So if you think of an up and down wave, like a sort of a sine wave type of motion, when one wave is at the crest, the other wave been reflected down the other leg would be at the trough, at the bottom, at the valley. And so you have one at the crest, one at the valley. If you add those two things together, you get 0. They cancel each other out. And all you have to do then is sit there like with a light sensor, waiting, hooked up to some kind of a computer, waiting for when all of a sudden you see a flash of light. That would tell you that you no longer have perfect destructive interference. That's the path length that the light has taken has been altered somehow. Now, how could you alter it? Well, one way you can alter it is have an 18-wheeler rolling down the highway nearby on an interstate, and the slight little tremors generated by that motion can shake the mirrors such that the path length has changed in such amount that we no longer have perfect destructive interference. Remember, we're trying to measure changes, that is stretching and squeezing of space, that's on average about 1/10,000th the size of a proton. So these are very, very, very short length scales that we're trying to measure. Now, one of the ways you can prevent that false detection of being caused by an 18-wheeler or not a gravitational wave is, of course, isolate your mirrors. And that's what was done for many years, figuring out the engineering so that we could isolate our mirrors not only from earthly disturbances such as 18-wheelers, but, from the normal tremors and earthquakes and all of these things. The Earth turns out to be a very noisy environment for these gravitational wave detectors to be operating at. So you want to make them as if you like, shrouded like noise canceling headphones in some sense. You want to make them less sensitive to the noise as much as possible. And the only thing you want them to be able to do is to detect true gravitational waves. Now, if you do detect something, how do you know it's real? Well, it would be nice if you had another detector located somewhere else, so it's not going to be affected by any type of local disturbance. And if that detector also detects the gravitational wave, then chances are it's probably real. So the National Science Foundation, as well as scientists, at Caltech and other places, got together and built what we call the Laser Interferometer Gravitational Wave Observatory, LIGO for short. They built one down in the state of Louisiana and another one in Washington State. And the ideal was that if a gravitational wave then triggers one of these detectors, then calculating where the wave is coming in from and it travels at the speed of light, you then know how long it would take for then this disturbance to hit the secondary gravitational wave observatory. And if the timing was right, such that it is passing through the Earth at the speed of light, remember the Earth doesn't stop it, right? It passes right through at the speed of light, then you know that it's consistent and you can be fairly sure of the detection of a gravitational wave. In fact, this is exactly what happened back in 2015. First, the detector in Louisiana went off, and then the one in Washington State went off. And it went off in such a way that it signified the detection of a gravitational wave. And from that detection of those waves, you can then determine what is the progenitor of the waves, what caused this source to hit us, this burst of gravitational waves. And in that case, it was the merging of two black holes, binary black hole system. Now, it turns out you can take, Einstein's general theory of relativity and apply it to different situations. Instead of having two black holes, let's say, of 50 times the mass of the sun, imagine you had one that was 30 and one that was 40, or one that was 30 and one that was 100. And you can go all through all these different scenarios and combinations of different masses for binary black holes. And you can extend that even to, other objects like neutron stars, for example, merging together, or a neutron star merging with a black hole. And through the simulations, you can calculate, if you like, what would be the predicted waveform. That is, what would the burst of gravitational waves actually look like when we detect them. And then we can work backwards and say, okay, I have this detection of these gravitational waves. I don't know what caused it. Then you can run through your whole library, essentially maybe of millions of combinations, looking for the best match. And that's essentially what you do. You do that sort of thing. So we use supercomputers to do these calculations, to create that library of waveforms, as we call them. And we use, numerical general relativity as sort of the heart of producing these libraries of waveforms. Now, what's interesting here in this case is that there is going to be a new release of these gravitational wave sources coming up very soon, in the next few days or a couple of weeks from now, where the scientists are saying that they have detected an additional 128 new gravitational waves sources. So these could be anything from massive black holes to neutron stars, maybe even a white dwarf colliding with a neutron star, or maybe a white dwarf colliding with a black hole. So this would essentially double almost the amount of gravitational wave source that we detected since 2015. So therefore, in sort of a time frame of roughly 10 years or so, we've detected essentially hundreds of these gravitational wave sources. And the interesting thing also about this, don't forget, let's imagine you have two black holes. And these black holes, and it doesn't matter what their mass is, let's just give them the same mass we've used all along here, 50 times the mass of our sun. If these black holes are by themselves, isolated, they're in orbit around each other, but they have nothing around them, no type of normal material. They'd be what we call naked black holes. When they actually spiral in and eventually merge, and you get the burst of gravitational waves, you don't get anything else that's released. You don't get any type of light signature, what we would call an EM wave, electromagnetic wave. You get nothing. There is no burst of ultraviolet or gamma rays or infrared or radio waves or optical light. Nothing would come from the merging of these two black holes if they are totally by themselves with nothing around. All you would get is this burst of gravitational waves. In other words, we would never realize that this event actually happened, the merging of these black holes, unless we were able to measure the burst of gravitational waves. That's the only signature that would get released. Okay? So this opens up really a whole new window on the universe where things that otherwise would be invisible now become detectable. And of course, we can study a lot more of these objects through further understanding of how nature actually works. So it's very, very interesting overall. Now, speaking about interesting things, what came down recently is a paper that was published. This is a preprint of the paper. And just to read the title here, MeerKAT discovery of a high redshift strongly lensed hydroxyl gigamaser. And you might wonder, what the heck is this all about? Well, first of all, most people are familiar with a laser, what that is. Now, just to kind of jump ahead a little bit, so let me go to this slide here. Here's a way to kind of think about it. In this case, we're dealing with a maser. So a laser is light amplification by stimulated emission of radiation. The maser is the microwave amplification by stimulated emission of radiation. But essentially works kind of the same thing. Now, there are natural masers that we find usually associated with star formation regions. And what we're showing you in this slide is, if you think of electrons as they're different energy levels as they orbit around the center of an atom, for example. And we can think of these orbital levels like rungs on an energy ladder in some sense. So the bottom rung of the ladder is the lowest energy state. If you go up one rung on the ladder, you're up to a higher energy state. If you go up another one, it's an even higher energy state, and so on. It's kind of like a ladder here on Earth, right? If you're doing something to the side of your house, if you're on the bottom rung of the ladder and you fall off, it's like ho-hum, you're not going to get hurt because maybe that rung is only a couple inches above the surface of the ground anyways. But if you're up, 6 rungs up the ladder and you fall off, then you're talking about something different. In that sense, you can think of it as the potential of damaging yourself or hurting yourself is greater the higher up you go. And you can think of that in terms of gravitational. Are people hearing me, by the way? This is not pre-recorded, so somebody asked a comment in the chat, pre-record. I just want to make sure everybody's okay. Can you hear me as I'm speaking here? Just give me a message maybe in the chat. Okay, anyways, so what happens is that, okay, let me do something here. I want to make sure that we're broadcasting. Not unusually. Not usually. Okay, let me see. Sorry for the interruption here, so I'll double check some things. Okay, so you can hear me, good. Okay, so what's happening here is that normally an electron, for example, in an atom wants to be at the lowest energy state, which we call the ground state. That is at the lowest rung. And in general, you can think of that systems in nature is the same way, that a lot of systems want to be in the lowest energy state. Now, what can happen is under the right condition, you can cause electrons to be, if you like, transition to the higher energy state. So in the slide that I'm showing you here, it's known as pumping, for example. And so you can pump electrons, that is, you give them energy so they populate a higher energy state to the point where the population in those higher energy states actually is greater than in the lower energy state. Remember, a system tends to want to be in the lowest energy state. You can use that argument to say, okay, why does a pendulum bulb, for example, if I pull it to one side and let it go, it swings back and forth, and then because of the friction and air resistance, eventually settles down to the bottom. Why doesn't it like go up to the top and stay there if it was like a rod attaching it from the pivot point to the bulb mass itself? And that's because hanging downwards is the lowest energy state, and a system tends to want to be there in general. Now, what happens in this case is that we can, in some sense, artificially, if you want to use that term, cause more electrons to be found in the higher energy state than in the lower energy state. And with the right photon that comes along, and that photon usually has the frequency or the wavelength that gives it a characteristic energy of the energy difference between a state that the electrons now are populated in and where the electrons want to go, a lower energy state. You can cause those electrons to jump down to the lower energy state. And if you do it to one electron, you might cause two electrons to drop down to a energy state, let's say energy state 1. Both of them will release a photon of the same wavelength and potentially the same phase, as we say, that is the crest line up, crest to crest, drop to drop, and so on, and going in the same direction. And they would hit an atom that also has the same kind of population, if you like, mixture. So they would each release photons, and it's like a chain reaction, 2 to 4, and keep going like that. And all of a sudden you have a huge number of these atoms then that are releasing light with all essentially the same wavelength and amplitude. And that's the sort of lasing effect that we're talking about here. That's, a really rough idea of how a laser works in general. But like I said, it's not just lasers that do this. There's also these masers. Now, masers were discovered for many decades. It's not unusual. But the interesting thing about this study is this is the highest redshift maser that's ever been discovered. And there's kind of an interesting way of how this was discovered, and I'll mention here in a second. Now, the distance to this galaxy that has this maser, the distance, and you see there in the title, it says highest redshift Z equals 1.027. Now Z, then, that represents a distance of about 8 billion light years. 8 billion light years. So this is now the record holder. This is discovered in the radio by MeerKAT. So MeerKAT, you think of that animal, okay, but this is not what we're talking about here. MeerKAT is interesting. It's actually the combination of radio telescopes that are located in South Africa. Here's an image of the part of the array. It consists of 64 radio telescopes. There's an interesting kind of story behind this. There were plans, and I remember being in graduate school way back in sort of the early 2000s. There were talk about different countries, because it was so expensive, coming together and build what they call the square kilometer array. So it essentially would be an array of radio telescopes, that is a collection of radio telescopes, located in the same general area, spread out over an area on the ground that's equivalent to 1 square kilometer. And you might wonder, well, what would that give you? Well, number one, the more radio telescopes you have, the more collecting surface that you have, light gathering ability, as we say in astronomy, so the fainter you can see, therefore, at radio wavelengths. The other thing you get is if you spread these radio dishes over a very large area on the surface, you get a much higher resolution. So the resolution depends on how the baseline in which these radio telescopes then, are spread out over a certain area. The larger that area, the higher the resolution you can observe that. And that's why, for example, when we made observations with the Event Horizon Telescope, for example, we saw the shadow, if you like, of the supermassive black hole that's at the center of the Milky Way. Those observations were only possible to have that very, very, very high resolution because the radio telescopes that were taken part in the observations were spread over essentially the size of the Earth. In that sense, the Earth acted like one radio telescope in terms of the resolution. Okay. So there are many advantages then of having arrays like you see here. Now, when these if you like, observatories, the square kilometer array, is predicted to cost a lot of money. And you're talking well over, I don't know the last figure that's put on this, but it was well over $1 billion. So that's a lot of money. And so much money that not one country was willing to cough up the money to pay for the project. So it was divided amongst a couple different countries. And the other thing you have to decide is once you say, okay, we got the money, we're going to build this thing, where are we going to build it? Okay. Are we going to build it, in one country? And if we do, they get all the work, right? They get all people employed for a number of years to build the system. Shouldn't they pay for it? Why do I need to pay for something that's built in some other country? There was a little bit of that. In other words, politics was involved in all of this. So what ultimately happened is we built smaller arrays, if you like, just to prove the technology a little bit. And one of them was built in South Africa, which we call MeerKAT, and the other one was actually built in Australia. And so we're going to actually combine those two arrays together when you're observing something as part of the whole square kilometer array. So the square kilometer array, its initial design has changed significantly from what we are thinking about today. But we're still in the process of kind of figuring that all out. And it's mostly a money thing, right? These things cost a lot of money. So the particular observation of this maser was done with the telescope array that's in South Africa. Now you might wonder then, how do I see something that's, 8 billion light years away? That's not around the corner, right? That is, more than halfway across the known observable universe. So it's not something nearby. And how they're able to accomplish this feat is actually use something that we call gravitational lensing. And this is the key in this. Now, the presence of mass, or you can think of it in terms of energy or even pressure, that warps space and alters time, right? We always think, since Einstein, special relativity, space-time is united into one, right? Things that can affect space and also time at the same moment, if you like. So the presence of mass, like a galaxy somewhere in space, can alter time, around that compared to something that's much further away from that galaxy. And the other thing it does is it also alters space. It actually can curve space. And when light from a distant source, a background source, is traveling through the emptiness of space, that light wants to follow a path called a geodesic. We can use that term, right, on this podcast. And if you're in the middle of nowhere, if you like, where there's no other mass around, that geodesic path is a straight line. It's flat. Just like you were traveling, if you were a bug fixed to the surface of a table, that spatial curvature of that table to you is flat. But when a ray of light passes near the vicinity of an object with mass, like a galaxy, all of a sudden the space it's traveling into, or through, if you like, is no longer flat. It's no longer flat. It's actually curved. And that would change or cause a deviation in the path of the light as it passes through that region of space. Now, what we can do, if in this way of thinking about it, is taking like a lens. And if you take a lens, or better yet, an example, take a glass that you drink from, a drinking glass, and make sure it's empty, of course, tilt it up, and then look through, let's say, the top of the glass towards the bottom of the glass, and have the glass pointed at a light source. And then first of all, move it away from the light source, and then across the light source, and then continue to go on the other side. And what you'll notice is, as you pass the bottom of the glass by the light source, you'll see this sort of optical distortion of the light. And in fact, you could even see at some alignment a nice ring going around the bottom of the glass. That's kind of like what the presence of mass does, and its effect on light rays that are traveling essentially from behind the galaxy relative to our point of view through the vicinity of the space around that galaxy, and then ultimately those rays of light hitting us here on the Earth. So the presence of a galaxy like that can even magnify, act like a lens in that case, of what we see in a space way behind the lensing galaxy. And what's happening is we can use the presence of these galaxies just in some sense like a magnifying glass, or like a better way of thinking about it is like a natural telescope. So the gravitational lensing feature then can actually allow us to see things that would otherwise be, let's say, invisible or very hard to see, allows us to see much greater detail because we can magnify the image of a much more distant object. Now, in this slide, that's what you see here. You see the radio dish on the bottom right, and it's observing a galaxy that's way behind the galaxy that's responsible for the lensing. So the lensing is sort of that middle galaxy you see there, and the one that's off to the upper left, sort of the reddish color, that's the galaxy that contains the maser. And then that little insert that you see there, you can see a magnified view of what that galaxy looks like from Earth. And the reason why we see it in such exquisite detail is because of the gravitational lensing effect. And it's quite interesting. I remember when I was at the University of Toronto, there was an astronomer, a professor at the university who was proposing, this would have been probably around 1998 or so. He was proposing to do just this. He was proposing to look for objects that are in the background of galaxies that were closer to us, that were acting like this lens effect, and trying to understand the details of these very, very distant galaxies by using this gravitational lensing idea. Now, I think the proposal never got time on a telescope, but that technique actually became mature later on, and we use it all the time now. So, in some sense, that would have been the forerunner on this technology, which has proved itself over and over and over again. So, very, very interesting for sure. Now, that is the sort of the last I wanted to mention today. But of course, if you're interested in any of this gravitational lensing feature, if you're interested in physics, if you're interested in the general theory of relativity, if you're interested in trying to understand more about gravity, about black holes, or anything else in science, of course, one of the things you can do is go to higher learning. To take classes from the University of North Dakota. We have classes both online and on campus. And so hopefully we have a lot of programs, not only in the STEM field, but also in other fields as well. I mean, we do have an English department and so on and so forth. And so it's very important to have people in different, if you like, disciplines, so all working together. And that's why we call it a university, right? That's where the name ultimately comes from. And so it's important to have people fill out those spots, if you like, in all different subjects, not just in the STEM fields. Now, if you want to listen to us, then we will, in a future podcast, we will be broadcasting live, hopefully back to our regular sort of situation. Robert will be here and I'll be in a different room. Right now I'm in my office, and of course you can't tell that. So our next podcast then will be a week from today, so that's on March the 17th. Now, one of the things that we always do is we leave you with a quote. So today's quote is actually by a very famous astronomer, Harlow Shapley, who passed away back in the 1970s. And his quote is, "No one trusts a model except the man who wrote it." Now, of course, today we'd say the person who wrote it. "Everyone trusts an observation except the man who made it." And hopefully you appreciate that. That's the uncertainties that we have in anything that we do in science, of course. So hopefully you'll like this podcast, and we'll see you next time. Please remember to give us a thumbs up. Thank you very much.